Today's lesson is on the altitude on hypotenuse theorems. So we're going to talk about, like it says in the objective there, the relationships between the parts of a right triangle when the altitude is drawn to the hypotenuse. Okay, so you have to have a right triangle to start with. This does not work with a triangle that's not right. And then when you draw on the altitude, you split the right triangle into two triangles that are similar to the original triangle. So you have three similar right triangles in the picture, and that is the reason that we have these relationships. Because again, when we have similar triangles, corresponding sides are proportional. Okay, so we're going to take a look at three different scenarios, and then we'll kind of recap it at the end. So the first one here, so it says triangle ABC is similar to triangle DBA. So triangle ABC is the big one here, if I highlight it in green, and triangle DBA, so DBA is this one on the right. Okay, so if you need to, what I would recommend is drawing them separately, pulling them apart, again, if need be. So again, if the big triangle here, this is the big one, so A is my right angle, let's put B on the right, and let's put C at the top. So then if it's similar to that little pink one, so again, my right angle would be at D, okay, we're going to put B here because angle B is in both triangles. It would be congruent to itself by reflexive. And then that would imply A at the top. Okay, so again, if I pulled them apart, this is what it would look like. So it says to write a proportion involving AB. Okay, so if you think about it, my proportion would be like AB to DB equals CB to AB. Okay, so again, or a different version of that. So we could have BC to AB equals AB to BD. Okay. Now, again, when you have a proportion, you can use cross products to solve. So if I multiply diagonally, I would have AB squared equals BC times BD. Okay, so in the picture, AB is a leg of the original right triangle. Okay, that's equal to BC, which is the whole hypotenuse. And then BD is the piece of the hypotenuse adjacent to that leg. Now, sometimes people say that's why I have this written down here, it's the original, one of the original legs squared equals the hypotenuse times its shadow. So if you think of it that way, again, AB would be a leg. Okay, the whole hypotenuse would be BC, and then the shadow of this particular leg, AB, shadow would be on the ground, so that would be BD. Okay, otherwise, leg squared equals the whole hypotenuse times the piece of the hypotenuse adjacent to that leg. So out of BD and DC, BD is the one next to AB, that leg. Okay, so let's give it a try here. So if we take a look at my two examples below, the first one says to find EF. So EF is a leg. Oops, let's try it with a different color there. That's a leg. Okay, so again, leg squared, so x squared is equal to the hypotenuse, which the whole hypotenuse in this case, 4 plus 6 is 10, times the shadow of the leg would be on the ground here, which is 4. Or, again, out of the 4 and the 6, the 4 is the one next to that leg. Okay, so if we multiply here, so we're going to have x squared equals 40. So to solve for x, we would take the square root of both sides. 40 is not a perfect square, but it is divisible by 1. 40 is 4 times 10. So my answer would be 2 square roots of 10. Now I know we focused a lot on when you solve a quadratic, you're going to have two possible answers, plus or minus. In this case, our x is referring to a segment in the picture, so segments cannot be negative. That's why I didn't focus on the negative 2 square roots of 10. Okay, on the next one, it says find RQ. So I'm going to let RQ be x. So again, according to our little conclusion here, the leg squared. So if I look at my picture, which one is the leg? We know the leg is 10. So 10 squared equals the whole hypotenuse, which is x plus 21, times its shadow. So the shadow, this is my leg, the shadow of the leg would be this x here, or out of the two pieces, the x of the 21, the x is the one closer to the leg of 10. So again, if we multiply this out, we're going to have 100 equals x squared plus 21x. So think back, I had you practice solving quadratics earlier. This is y, so we're going to get the equation equal to 0 so we can factor. So we're going to have x squared plus 21x minus 100 equals 0. So I'm looking for two numbers that multiply to give me negative 100 and add to give me 21. That's going to be a positive 25 and a negative 4. So when I solve it, I get x equals negative 25 or x equals positive 4. I can't have a negative segment length, so my answer is just 4. Okay, so again, your leg squared equals the hypotenuse times its shadow, or leg squared equals the hypotenuse times the piece of the hypotenuse adjacent to that leg, whichever works better for you. Okay, so let's take a look at two different similar triangles. In this next picture, assuming my technology here kicks in, there we go. We have triangle ABC, the big one, is now similar to triangle DAC, the one on the right. So again, the big one is ABC. The little one on the right is triangle DAC. So again, if you need to, draw them out separately. So again, here's A, let's put B here and C, and then the one on the right angle here is at D. Notice angle C is congruent to itself by reflexive, so C would be at the top. That means that A would be over here on the right. So triangle ABC is similar to triangle DAC. Now it says to write a proportion involving AC. Okay, so if we look at it, we would have AC, it goes with DC. So again, here's AC and DC, and there's another ratio that involves AC. Notice AC and BC. So if I put this AC on top, I need to put BC over AC. Okay, so cross products would tell me that AC squared equals BC times DC. So again, according to this, AC is a leg of my original triangle, my original right triangle. So the leg squared is equal to, again, the hypotenuse, which is BC, times its shadow, which would be DC. Okay. So leg squared equals hypotenuse times shadow. Like I had there, AC squared equals BC times DC. Okay, so again, works for both legs. So the leg squared equals the hypotenuse times the shadow of this leg, which would be DC. Okay, so if we practice a few more here. So again, this time I want to find EG. So let's call EG X. So again, my leg squared equals the hypotenuse, which is going to be 4 plus 6, which is still 10. And then the shadow of this leg on the ground here would be 6. Or again, out of these two pieces, the 4 or the 6 is the one adjacent to my leg. So x squared would equal 60. So to solve for x, we would take the square root of both sides. 60 is not a perfect square, but it is divisible by 1. It's divisible by 4, and 16 is 4 times 15. So my answer for leg EG would be 2 square roots of 15. Again, it's not the negative because we're talking about segment length, and segment length has to be positive. Okay, so again, leg squared equals hypotenuse times its shadow, or instead of shadow, the piece of the hypotenuse adjacent to that leg. Okay. Okay, and then the last one, instead of looking at the big one similar to one of the two smaller ones, we can actually also say that the two smaller ones are similar. So it says triangle ADB. So ADB is this little one on the left. So let's just do ADB like this. And that is going to be similar to the one on the right. So again, my right angle here is at D. So this would be CDA. So it says to write a proportion involving AD. So if I look at the picture here, AD goes with CD. So AD over CD. And that is equivalent in a ratio to, let's see what else has an AD in it. Okay, DB goes with DA or AD as well. So then I could put DB to AD. Okay, so solving it, doing cross products here, we would have AD squared equals BD or DB times CD. So again, back in the original picture, my altitude is AD. So the altitude squared equals the product of the two pieces of the hypotenuse. CD and BD are those two pieces. Okay, so like I said, AD squared equals BD times CD. So the altitude squared equals the product of the two pieces or the two parts of the hypotenuse. Okay, so if we take a look at this picture, notice I keep coming back to that same triangle. So the altitude I want to find is EH, so we'll call that X. Okay, so the altitude squared equals the product of the parts of the hypotenuse. So the two parts of the hypotenuse are 4 and 6. So X squared is equal to 4 times 6. So again, to solve for X, we would take the square root of both sides. Well, the square root of 4 is 2, so my answer is going to be 2 squared to 6. Okay, so what we're going to focus on today, and then we'll just practice a few more tomorrow, is these different theorems, these concepts. Now, these are actually theorems that we discovered looking at the corresponding sides. But again, just kind of wrapping it up in terms of words. If an altitude is drawn to the hypotenuse of a right triangle, then the two right triangles formed are similar to the given right triangle and to each other. The altitude to the hypotenuse, that was the last one we looked at, is the mean proportional between the segments of the hypotenuse. Okay, and then either leg of the right triangle, of the original right triangle we're talking about, is the mean proportional between the hypotenuse of the given right triangle and the segment of the hypotenuse adjacent to that leg. So again, these are the theorems in terms of words that we had discovered looking at the similar triangles. So for today, and tomorrow for that matter as well, tomorrow there will be a separate worksheet. Today you're going to do the day 1 worksheet, just practice finding a leg, the altitude, or maybe a hypotenuse or part of it using these theorems. And then the next day we will take a look at just some more problems to reinforce this idea. Have a great day.